Testing. I think the stream started. Okay, so my mic is really low for some reason. Test. It should be better. Test. It should be better. Okay. I'm going to start now. I think I scaled everything properly, but I should probably be starting with something. I'll start with how it's made. So not really the code today, but how to make it. Uh, Sorry, it's taking a bit long to set this up. Alright, I think that's should be fine. I'm not sure if it looks fine on stream, but okay. So I'm just gonna wait to check something here. Yeah, okay, it looks fine. So this is how a Raytracer works essentially, and if I remember correctly, because I haven't done this in so long, unbelievably long, like 5 months, I don't know. So, well, first it's probably best to explain what array is. So you can think of array as like an arrow here. It starts from one place and it goes here. I draw an arrow here, but it actually goes on infinitely. So you can just imagine like starting from one point and giving it a direction, and it'll go infinitely in that direction. So let's say I had a 2D plane here. So let me just get rid of this stuff. Let's say I had a 2D plane. I could start array at like say the origin, and I could start it at the origin and give it some sort of direction with what's known as a vector. It has a length of 1, and that would mark it as sort of, this is the start, this is the direction, and it's going to go infinitely in that direction, right? So let's say this was 2D, not 2D, 3D. Let's say I had another axis. If that looks kind of 3D. I could start it from anywhere, and I could have nonsense right now. So how does this have to do with ray tracing? So in the real world, we have a camera. You can imagine it as just an infinitely small point, and we have light, which usually isn't infinitely small, but we can say it is. And here, one sec, let me change the size. And like objects, so pretend this was a cube. So what would happen is all these light sources, depends on how the light actually, what type of light it is, but let's say it's directional, so it only goes in one direction. You can imagine a ray, essentially a ray of light, hitting an object, bouncing off of it, and let's say it's spherical, so it actually hits its spherical light, so it'll output rays in all directions. So some of these rays will actually bounce off an object and hit this camera, and that's essentially what we see. We see those rays hit an object, bounce off. That's how nature works. But you can imagine that sending out all of these rays and calculating which ones hit the camera and then displaying them, that's a lot of calculations, and it's unnecessary because for the most part, we only have one camera. We only need certain rays. We don't need to calculate this ray over here. We don't need to because it's never going to hit the viewer. So instead of doing all this where we take the light source, this is L for light source, and shooting out all these rays and letting them bounce off and all that, and then some hit the viewer, what we do is we actually shoot the rays from the viewer. So let's say this right here is the FOV, the field of view. We would shoot rays in all these directions, and someone hit objects and all that. We could calculate that, but we would only calculate them if they hit the light, because that can be traced back. That can be traced back to the viewer, so you know which areas are supposed to be lit or not. So, one sec. Maybe I can clear this easier. Control C. No, I don't know, paint. I'm just gonna make a new one. Okay, I'll erase it manually. I need to learn how to actually use paint. Yeah, it's not working out well. One second. Okay, I found a way to actually use paint. Okay, so let's put this into coding terms a bit. So we'll have a single camera, and we can call that camera C. And all this camera is going to have is a position, which is actually a good time to speak about what a vector is. So a vector in our world, since our world is 3D, is going to have three components, an X, a Y, and a Z. And this is simply what it is. You can imagine it as a three-dimensional array with three values here, and these can be anywhere from negative infinity to positive infinity, and they determine uh, where space is. I do sound dead. I need to look at the chat a bit more. And I also need to sound less dead, but I'm trying to be quiet so I don't disturb people. Uh, so you can imagine this as a camera. See, it'll it'll have some properties we'll define in the code, but for now it's I can show you actually. For now, if we actually look at what the camera is in our scene, it's got a lot of nonsense here, but the most important part is where it is and where it's facing. All of these other stuff we can calculate through that. And there's also like the FOV, the aspect ratio, but these we'll go into later. For now they're unimportant. We can just think of the camera as a position in space, a thing in space, and it's looking at somewhere. So camera here, right? The position will be defined as x, y, z. So let's say it's at the origin. It's at 0, 0, 0. And it's facing directly in the x-axis. I think that's the x-axis. This is the y, and this is the z. But let's say it's facing directly in the x-axis. So how do we represent this facing attribute? Well, we can represent position and facing. We'll call it not facing, we'll call it direction. So it has a position and it has a direction. And let's say this direction is simply um, it's facing the x-axis, so the direction will be 1, 0, 0, right? And if that seems a bit I don't know, confusing at first, why it's 1, 0, 0, you can take out the z-axis here, and you can think of it as just the plane again, the 2D plane. If we had a point on this plane, that would be at 0, 0. And if we had a direction like this, we can just mark this direction as another point. So this is the position, this point, and this is the direction, this point. And those two things create a vector. So the direction is simply x1, y0. I'm not going to draw 0 here. And the position is 0, 0. And the same for 3D. Let's say we had a direction that was not here, but a direction that was here, facing directly at Z. And let's say this was at Z equals 1. So instead of 1, 0, 0, we would instead we would have 0, 0, 1. That would be our direction. Because over here, Z is the last attribute, and this is the z-axis. So that's just basic vectors. If we look at the code, and in vectors, there's a lot of functions here. There's a lot we can do with them, but the constructor, the actual vector itself, only has three attributes. It has x, y, and z. Because really, a 3D vector only has three attributes, x, y, z. So it might actually be a good time to talk about what you can do with these. And there's a lot of math here, but it's the basis for everything else that's to come. We're writing functions here so that we can use them later in the actual Raytracer. So these are everything that needs to be used. So I guess we can start at the top. These are actually pretty useless. I'm not sure where I use them. This just reverses the sign, so it makes it negative. Takes the current vector and makes a new one. Return new. VB is a bit different. I'll go into that when I discuss how I implemented color. Add just adds two vectors together and returns a new one. Subtracts, same thing but for subtracting, same thing for multiplying. Now this one's very important. It's called magnitude, and I'll explain why it's important. But if you see here, it's just taking the hypotenuse. And I'm going to explain why this is important right now. Okay. Gotta get this up. Okay. So this is why it's important. When we work with vectors, specifically in the Raytracer, we need to always have them have a length of 1. The reason is for this is slightly complicated, but it's due to something called normalization. There are two types of normalization, but there's one type. I've confused it with something else, but there is one type of normalization, and what normalization means is we can take a vector of any length. Let's say this is a vector of length 7.2, and we can take the direction. We can keep the same direction, but we can make it so that its actual length, its magnitude, is 1. And that's called normalizing that vector. We're normalizing it to a length of 1. And so why we're using hypotenuse here, that hypotenuse, is because in order to normalize it, right, this vector, it's not a direction. We don't represent it as a direction. We represent it as an x and a y. And this sort of forms a triangle, right? So, and this is a right angle. So we can take this x and this y, and we can find the hypotenuse, right? And if I remember correctly, I think I clipped something here. Okay. If I remember correctly, x squared, we can find the hypotenuse, right? We can find the magnitude. That's not y squared. I'm not going to represent this as z squared. I'm just going to represent this as magnitude squared because we're using z for something else here. So we can get 7.2, right? But if we go back to the normalization function, the reason why this magnitude is here, norm, what we do is we find the magnitude, and then we get something called, we get a divisor, which is set to 1 over magnitude, and we multiply that by our current vector. So I'll explain what that looks like. in a second. Alright, so this is, let's say we did 1 over magnitude. So actually, let me write it here, 1 over 7.2. And we run the multiply function, which scales our vector down by multiplying each aspect by this. So let's say we scaled our vector. What this would do is it would scale the length of it. It would scale it down. 1 second. Okay, it would scale this, which has a length of 7.2, and these cancel out, and now it should have a length of 1. So by scaling the x and the y, it'll essentially scale down this entire equation, and it'll scale down the magnitude as well, so that what we are left with is a new vector with a length of 1, but the x and the y, they're in the same ratio, so it still has the same direction. I'm not sure if I explained that completely well, but it'll make sense later as I show exactly what this multiply is doing. Now there's a bunch of other functions here. Dot function, multiply vectors, cross function. The math behind them I never really understood, but I know their function. And for now, that's going to be enough. You can sort of, I guess you can look further into what these are actually doing by using these values, but for me, I kind of just researched them, plopped them in, and used them where they were needed. So I'll explain what the dot function does. The dot function, I'm pretty sure, don't remember exactly, but if it jogs my memory, 1 second. Okay, so the dot function's a bit weird. I don't remember exactly what it does, but I can explain why we use it. The dot function of a 90-degree angle of a vector, here, two vectors, vector 1 and vector 2. The dot function of this 90-degree angle made by these vectors is going to be 0. And if two vectors were exactly the same, or actually parallel, their dot function, I guess, between them would be 1 if I remember correctly. So it might actually have to do with like cosine and all that, but it's not important for now. It's mainly used to find shading, because if we have light coming from this direction, say this is a light source, and actually I'm gonna take a lot of this out because it's clogging stuff up. If I remember how to. Okay. Alright. So let's say I have a light source. up here, and the viewer is over here, and there's an object. So this exact point, this will have a scaled color value of 0 because the light and the viewer, the direction from the light and the viewer are perpendicular basically, so you can't see anything. And but let's say the light was right behind the viewer, it would be scaled, go back like that, and the viewer would be able to see as much light as possible, so it would have a scaled value of 1. uh, I think that's it. I'm not all too sure. Again, I've forgotten a lot of this, but I think that's what it's about. Alright, sorry about that. Um, let me, where was I? Cross functions, so it's cross is like finding, let's say I had a vector like this. Oh, you're looking at the wrong thing, I'm dumb. So let's say I had a vector like this, and I had, yeah, that. A cross function would find perpendicular vector. And in 3D space too, so if I had a vector like this, it would find this one. Even though there's two perpendicular vectors, it would find the one essentially in this order. That's just how it works really. So from z to x axis to y axis. And that's essentially it for vectors. That's a lot to take in without exactly knowing what that's all for, but I think I should start explaining how the ray trace. Well, I kind of explained how the ray tracer would work, but there's two parts. There's the first part, which is simply taking like this viewer. He has a certain canvas like that. I think my drawing's fine. And each, you can see this canvas, if I draw it out here, it's just a simple rectangle. And for each pixel here, so I'm going to draw the pixel a bit exaggerated because it's very hard to see a single pixel. But let's say for each pixel here, it'll calculate where that pixel is in 3D space, because remember, this is 3D. So it'll calculate the position here from this 2D pixel. And what it'll do is it'll shoot a ray through that pixel out into the scene. And if that ray bounces off of any objects, it'll calculate, so like, let's say there's an object here and this is a sphere. Or actually, to make it easier, let's say this was a square. That's not a good square. It would hit that square, and a calculation would be made between the square and it would bounce off, and the ray that's shot at it, and it would bounce off, maybe hit a light, and if it does hit a light, then that would be detected, I guess, and you could explain that yes, there is a value here. We don't know what the color is, we don't know what its shade is, but we know that it intersects somehow and hits a light, so there's an intersection and something can be done with it. So actually, if I bring up the Raytracer here and actually go into the main file, we have a bunch of functions here. They don't matter, but we have the shoot ray function, and we check if there's an intersection, we need to run a shading algorithm. But let's say that we took the shading algorithm out and we just ran it as it is. And instead of returning values from shade, we simply want to know where stuff is. So if there is something there, then we're going to return the hex value, the RGB value for white. And if there isn't, we'll return it for black. So we just want to see if there's an intersection by running these algorithms, checking for intersections, blah, blah, blah. And if I run this here, I think this is how to run it. I kind of forgot. It's going to take long because this is a long process. It takes a lot of computing to check all the intersections, but it's running. Let me set that up for you. I think I'm just gonna put another, not really familiar with OBS, but I think I just need to do this, right? Or what I searched up there. And wait for this to run. Should produce something. Now I'm not completely sure when it's going to actually finish, but hopefully it does. I might try doing this as well. I'm gonna just wait for it. This is very exciting. We get to wait for this to never load. And also crash my browser. Yeah, I think the tutorial would be better in video format. I agree. I'd have a little more time to actually get this to run. So you're just gonna have to wait for these tabs to finish running. I think I'm gonna take this one out here and just try. In the meantime, I don't know. I don't know how long it takes. It usually takes like 2 minutes or so to actually produce anything. I'm gonna start setting some stuff up in Paint while it runs. Maybe it'll actually finish at some point in time. If it doesn't finish soon, I guess what I could do is run it without all these extra fancy algorithm things. But I'm kind of confident it'll actually do something. I think it's gonna. Yeah, I don't know. I'll show this for now. Okay, so before I said that we would have this object or something, a camera, and it would point, and somehow we just magically know where this would bounce off of, and that's not really the case. There's a lot of math that goes into checking for intersections and all that, and it's going to be much easier to explain if I do it sort of in 2D. So I'm going to give the analogy of, let's say we had a flat ground over here, and like the ray, we would have a tennis ball. I can't draw, but that should suffice. Yeah, a tennis ball. And it would hit the surface, right? And you can kind of tell where it's gonna bounce because we know what direction it's going in. But let's say for a second, what if I change this ground area? What if I made it instead of like this, I kind of that's not good. What if I made it like that? Or actually better yet, to make it a little easier to see. What if I made it like this? Now, we know that there's something wrong here. It shouldn't be bouncing in this direction. That's just not how it works. Instead, instead of this, it should be going some other way. Um, and we can calculate which way it's going because we know how the ground is facing. It's a little weird to put into terms. We know that it's facing this way, so logically it should be going that way. And there's a theme between this. We know how the ground is like angled, I guess you could call it. So we know it's perpendicular. We know this vector. Uh, and that vector is very important because with that we can find essentially intersections and how stuff is going to bounce. So we know that all across this ground, it's going to be perpendicular the same way. So even though it's perpendicular in this place, it's also perpendicular right over here. And I think with that, you can kind of tell where it's going because this angle right here is an exact mirror of this angle. And this is why this vector, this one in the middle, is very special. It's called the normal, not normalization, just simply normal. And that's important to keep in mind to separate those two terms. They're not the same. This is the normal of this, I guess, surface, this ground surface. So if we have the the original vector, the input, or in this case, it's going to be the viewer. So like a camera, I guess. We can, and since we have the normal, we can kind of calculate how this vector is going to bounce off. And we can see if that's a light source over here. And that's really the basics of it. It's just we shoot a bunch of input vectors out in a sort of function called in Raytracer here. You render to render the scene. We shoot a bunch of functions out by getting the direction of them and then shooting them out. And then we run a function called check for intersect. So we check if there's an intersection with our ray with a object in the scene. So let's say it was a plane. We could run this and we could see, is there an intersection point where our ray hits that, and then also what's the normal of that surface. A lot of information there, and we can supply that to our shader function, and we can use all of that and all of the algorithms essentially to calculate where light is, to get the dot product to see how much we should shade it, to get the color, and a bunch of other types of shading and returning a hit color. And then we just, for that pixel in the scene, all the way back up in the render function, we just fill it with the color that we're given. And that's the gist of ray tracing. So that's going to be the end of the stream, and maybe I'll edit it into a proper stream, but I'll be making more of these to go way more in depth in actually what these algorithms are, because this video, this stream was overview. It was an overview of everything. So next video, I'm going to explain how the get direction function works and how we can uh, turn these 2D pixels into 3D vectors. All right, bye.